तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This course is on digital circuits and digital systems. You see, this we have this signals. Signal is a variation in a parameter, physical parameter. Temperature variation is a signal. Speech, as I speak now, it's a signal. Video is a signal, it's a light intensity variation. Now, all these signals, any of these signals that you get need to be maybe processed to be available to the other end, maybe stored. So, you do a lot of processing of signals in real life. For example, take a microphone. The signal, the speech signal that you give into the microphone, if necessary, it needs to be amplified and then given out as a signal out of the speaker, the sound signal out of speaker. So, it's a typical signal processing scenario. Basically, a signal in the electrical, we are in the electrical engineering domain. We talk about only electrical signals. That means a variation of an electrical quantity, a voltage or a current, as a function of time. A signal is defined as a variation of a electrical quantity, usually a voltage or a current, with time. Of course, you can also have a signal which does not change with time, then it's not called a signal anymore, it's a DC value, we'll say. For example, if you know that the value is not going to change, there's no need for processing. You know that the value, so you can use the value wherever you want to use it. Now, once you have this variation, any signal that naturally occurs, like speech or temperature variation, or as I said, the illumination changes in the television, or a seismic earthquake activity, any signal, first you need to convert it into electrical variations. Some of them are mechanical, other parameters, other physical parameters. So, there is a transducer, a sort of a device, this device which converts a non-electrical quantity into an electrical quantity. Electrical signal is called a transducer. So, the output of the transducer is an electrical signal, where we define the signal as the variation of the parameter of interest, a voltage or a current, with time. Normally, a signal can take any value, of course, within a given limits, and at different instants of times. A signal varies continuously. For example, you have a time variation of a signal, voltage level of a signal with respect as a function of time. if I plot like this, there are any number of values this signal can take as a function of time, but of course it is always limit. What is the minimum of this? Let us call this minimum value 0 and maximum value V max. Two different values you define, two values you define and say that signal always varies within this range. This is the range of the signal. And at any instant of time it can take any value, and what is the instant of time is also not defined. I can make a measurement here and immediately at the very next instant of time, or I can do a measurement here and do it much later here. Nothing is defined here. This variation of signal which can take any value between these two limits, such a signal is called an analog signal. Analog signal or analog quantity can take any value at any instant of time within, of course, the limit defined, within the range specified. On the other hand, I want to process a signal only at discrete instant of time. Suppose I want to monitor the temperature of a system every minute or every hour or every 30 minutes, whatever. You discretize the time at which you look at the value of the signal. The signal will vary continuously all the time, but you are looking at only at the discrete instance of time, at discrete instance of time, at definite instant of time. Only then you are looking at such a signal. Supposing I put this value, I will have equal intervals for time. So I call this T0 or the starting level point, T1, T2 need not be equal. Just to make it explanation easier, I make it equal instance of time, equal intervals of time, like that. So I monitor the value of the signal V of t at instance of time T0, T1, T2, T3, T4, as long as I want, as long as I am interested in the parameter. Such a signal is called a discrete time signal. So a continuous variation signal still continuously varies. The analog signal only. An analog signal is a signal which can take any value between the two defined limits as a function of time. But even though the signal varies, I am only interested in looking at it at specific intervals of time. Such a signal is a subset of the analog signal. That is called a discrete time signal. The problem in these two cases, whether you want to continuously monitor, what is continuous? Finally it has to be discrete. Even if it is 1 microsecond, then what happens between these 1 microseconds? Even if it is 1 nanosecond, something can change in between these. Finally we can only observe. Physical parameter will vary, input, output, but if you become an observer, the observation can only be discrete. Is that right? Okay. But whether it is a discrete signal or a discrete time signal or an analog signal, the variation of the signal between these two limits is a continuous variation. There is no defined points by which it can vary. What I am saying is, supposing my initial value is 0 volts and V max is 5 volts as an example. As an example, I make this 5 volts. I am only allowing the signal to vary from change from 0 to 5 volts. Within this 0 to 5 volts, it can take any value. You may have difficulty in representing because of a limitation in the digits that you are having in your computer calculator, or I cannot represent any number beyond a particular number of digits to be meaningful. But theoretically, it can take infinite number of levels between 0 volts and 5 volts. Now, when you are trying to transmit a signal, because after all, what is the process of the signal itself has no meaning unless you use it somewhere. There is a change in this speech. I speak, my speech is picked up with the microphone, and converts into electrical signals. The electrical signal is amplified by an amplifier and then put out at the speaker, which brings it out as a speech signal. So there is a processing involved in any signal. If it's not processing, we are not interested in signal. We are not interested in looking at a signal just for the variation's sake. We don't want to stare at a signal just because it's nice to see. It keeps changing, so it's nice to watch. So I'm sitting and watching it like a wave in the ocean. You go to the beach and sit there and watch the waves. I like to do that myself. But that's only for fun, for relaxation. But when you have a signal, you have to use that signal some way. You transmit it or you store it for later use. One of the two things. I pick up the signal and process it and give it as an output to another system, another transducer, which will convert this signal into the physical parameter like a sound or a light or whatever. Or I may even store it and use it for later use. Suppose I want to know yesterday's temperature variation over today's temperature. 11 o'clock yesterday, what is the temperature? At 11 o'clock today, what is the temperature? I want to know at 11 o'clock I have to take the temperature reading, store it. Today I take 11 o'clock temperature, say it is hotter today than yesterday. So either you store it or transmit it. When I do that, how accurately can I represent my variations within this limits of 0 volts and 5 volts? As I said, it can take infinite number of values. I may not limited by the channel. How accurately can I send the signal? I can directly send it, at the output I can receive it, that will be an analog signal. But if you want to store it and reproduce it, I would like to be limited by the number of digits I want to use. That way I can say, I can safely say this is within that. Within that limit, I will define various levels the signals can take, and I will say the signal is in this level, tomorrow is in this level, there is a change of so many levels. So if I further discretize, I discretize the time to start with. Originally I had a signal with continuous time and continuous amplitude variation. Then I let the amplitude continuously vary but discretize the time. I am going to introduce one more discretization in the amplitude. I will say I will only let the signal take a specific type of amount of levels, specific number of discrete levels. So 0 to 5 volts, even though the signal is allowed to vary, the input signal I have no control. The temperature variation, when I record it, I only record it as discrete levels, or when I process it, I only process those discrete levels. When I transmit it, I will only transmit those discrete levels. Of course, how accurately I want the reproduction depends on how many levels I want to have. If I have only 2 levels, it is 0 or 1, 0 volts or 5 volts, the signal is present or not present. That is too crude. Or I can have 4 levels, 0 to 1.25, 1.25 to 2.5, 2.5 to 2.7, 3.75, 3.725. I can say signal is less than 1.25, I will say it is level 1. Between 1.25 to 2.5, I will say level 2. 2.5 to 3.75, I will say level 3 signal. 3.75 to 5, I will say level 4 signal. Then you know signal is in this range. Signal in this range. So more and more levels I introduce, I can introduce more and more accuracy in transmission and reproduction, but still it is a discrete level. So when I discretize the time in addition to discretizing discretize the amplitude in addition to discretize the time, I get what is known as a digital signal. So that means I will only allow this variations. Let us call this level 1, or this is at 0. I will say L0, L1, L0 will be level 0, L1, L2, L3, L4, etc. Depending on how narrow or broad these ranges are, the total number of steps will be decided. The total number of steps will be decided depending on the level of each of these steps I am going to take. Now I will say, suppose I want to represent the signal value at T1 It is between L2 and L3. I cannot say it is between L2 and L3. It is not possible to store between L2 and L3, or it is not possible to transmit between L2 and L3. I will have to either transmit L2 or L3. I have to make a prior understanding. I will always round it off to the nearest lower level or nearest upper level. So I will always, let us say for our example in this case, always round it off to the nearest lower level. I will say at T0 the signal is L2, T0 the signal is L2, T1 also the signal is L2, at T2 the signal is L3 because it is here, it has become between L3 and L4, right? At T2, at T3 it is L4, at T4 it may be L5 and so forth. So each of these levels can be stored or represented by a smaller number of digits than originally you had intended to be. Suppose I have infinite number of levels, I need infinite number of digits to represent it. Now each of these levels is going to have only discrete levels, no? So I will have fewer digits to represent and fewer for storing and fewer levels to transmit in the case of transmission. Now, so let us say there are only total of 8 steps between 0 and 5 volts. I divide this range into only 8 steps. I don't expect much variation in temperature, or I am not interested in too fine a variation. I want to know whether it is too hot today or too cold today. It is all right to know if I know where the temperature in this range of 0 to 5 volts. In 8 levels you tell me. If I tell you that, then I will use 8 levels. So these 8 levels can be represented by 8 different values. So it is easy to store 8 different values and transmit 8 different values rather than having to store infinite. Supposing this signal can be anywhere from 0 to 5 volts. If it is 4.7392489411, I should have so many digits to represent it or so many digits to transmit it. I am now removing myself of this. The accuracy that much is not required. On the other hand, I have the flexibility of increasing the accuracy by increasing the number of levels. If you are willing to store more levels and transmit more levels, you improve your accuracy. If you are not interested in storing more levels and transmitting more levels, that your application can now decide the accuracy that you want. So there is a flexibility in the digital domain which is not there in the analog domain. Analog domain, if you make a measurement, suppose you go to the physics lab, make a measurement of current or voltage. The representation is analog, the needle moves, it stays somewhere between 3.2 and 3.4, I mean 3.2 and 3.3, but you will only interpret it. It is 3.2 or 3.3 or say 3.25 or 3.275, like that you will make a guess. But really, if you want to be very, very accurate, I should need a very, very large meter with minor subdivisions of each of those and then keep on doing it till you can become very accurate. So there is an inaccuracy built in analog also. Because of our observation power, because of the limitation of the instruments we are using for measurement. Now I am legalizing it. That's all. I am making it official. So I am now saying I am going to tell you these are the levels permitted. Always represent your signal within these limits. When I give an analog meter, I approximate it. Here I approximate it in a systematic way. You understand? So now this is the digital domain we will be talking about. Now why do we go for digital? Because even though there is an inaccuracy built in analog also, if you want to improve the accuracy of analog, what will you do? You will do a more precise meter with a large range, and each range subdivided into many, many subdivisions, so that you will not make a mistake. Supposing you know the current has always had to be between 2.5 and 2.7, I will make a reading of 2.5 to 2.7 so large, between that I will divide into subdivisions, smaller and smaller subdivisions. It is possible to improve the accuracy of the meter any amount by putting more and more of precise instrumentation. By making a precise instrument for measuring current or voltage or whatever other quantity we are trying to measure, I can always improve the measurement of analog signals. Likewise, I can always improve the accuracy of my digital instruments also by having more and more levels, because I need to store more and more levels or to transmit more and more levels. So accuracy can be decided based on the application required. Then what is the advantage of going digital? So analog also has the potential inaccuracy which can be improved depending on the need by extra hardware, I will call it hardware, or extra precise instruments. That is what I mean by hardware. Put more money, in other words. If you put more money, you can get a better system, is it not? Anything. You get more money, you buy a better system. You get more money, you get a better car. Right? That is what it is. In digital also, I have a potential of improving the accuracy by putting more and more levels, which means more and more levels means more and more hardware. I should have some way of representing more digits, more levels. Earlier I had a fewer levels, now I have more levels. So I should have some other hardware to represent this. So here also it is going to cost a little more in terms of instrument implementation. But now why analog? Why digital? Then in that case, so this is the difference between analog signal, discrete time signal and digital signal. In this particular course, we will be dealing with digital only, both in time and levels, it will be digital. We are not talking about analog signal, that is analog electronics, POE, principles of electronics, we will learn later on, and discrete time we will learn some other time for some other specific applications. This course will deal with only digital signals and digital processing of signals, digital representation of signals, digital digitally how to store it, etc., etc. It's a digital course. It's a course on digital circuits and digital systems. Now, when you say that signals are basically analog in nature, by when it is generated, most of signals are analog. Temperature variations, you can't say the temperature should always jump from at 1 degree intervals. Can you say that? Today's temperature, you want to measure, can you say that my temperature can only jump from 31 to 32? In between you should not jump. Can you force it? No. You cannot. You need not take cognizance of the fact it is 31.2. You will say either 31 or 32, but then say temperature will change, analog. There will be infinite level it can take. It will only take 31.2745 also it can change. You don't know. Likewise, all signals are analog. Similarly, when you put the thing back on after processing or storing, transmitting, you get this back on the other transducer, reverse transducer in this case. In the case of microphone, the reverse transducer is loudspeaker. The signal makes the sound possible in the loudspeaker. Electrical signal is converted into sound. In the video, light is picked up as an electrical signal. It is processed, and in your picture tube at home, receivers, television receiver, the electrical signal is converted back into light, where you see all the shadows of all these movements which you are addicted to, right? All the time watching TV. So it is again a conversion of analog to digital to analog back. So why do we have to go through the digital path? Why can't we take analog signals? Anyway, there is an inaccuracy there. Digital also, the accuracy can be defined by you. Analog also, there is a provision to improve the accuracy by spending more and more precise hardware and more money. Digital also, I can do more and more hardware and then get better accuracy. So when that is the case, why suddenly make all of us learn this course, digital? One thing is I am going to get salary out of this course teaching you. That is a minor reason. The real reason is digital signals are easy to store and manipulate without much error. I will give you an example. Supposing I am measuring an analog value, I am storing an analog value. I store an analog value of, how do you store an analog voltage? How do you store a voltage? Capacitor. You store a value in a capacitor. Supposing I charge my capacitor to 1.27 volts today. Tomorrow somebody else comes and measures it. It is equal to storing and retrieving it later, or storing and transmitting it. you stored 1.27 volts, tomorrow somebody comes and measures 1.25 volts. Does that person know that you have stored 1.27 volts? If it knows, then there is no need for storing. You can also tell him. Then there is no need for a capacitor. If you are going to see that fellow, tell him it is 1.27, he doesn't have to come and measure. So when you leave a charge of 1.27 volts, voltage of 1.27 volts across a capacitor and measure it again, you don't know how much is lost. So analog value, because 1.27 is only our limitation, as I said, it can be 1.272, in that case it should be measured as 1.272. Whatever value is put, you should be able to measure it accurately. But there is always a leakage. Or I am transmitting a signal, an analog signal. Let us say same 1.72, instead of storing in a capacitor, I am trying to send it across a coil to other end as a signal. And that fellow, you try to send 1.72 volts. The receiving end, it is measured as 1.75 volts. This person has no idea that you send 1.72 volts. If you know that you send 1.72 volts, there is no need for a transmission. So the fellow, the other end, receives it as 1.75 volts. He is not sure what you sent was 1.72 volts. There is a 0.03 volts noise which has been added in the transmission path, which results in 1.0, but he doesn't know exactly how much is the noise added. Now, there is a uncertainty about the values of storage and the transmitted signal in an analog domain. Take a digital example. I have only 8 levels, as I said, or minimum number of 8. Whatever is the number of levels, I will take 8 as an example. Between 0 and 5 volts, I have 8 levels. So when you divide 5 volts by 8, what is how much is each step? 0.625, right? So if the voltage is less than 0, voltage level that I want to transmit is between 0 and 0.625, I am going to send it as a 0 level. That is what I told you. I am going to round it off to the lowest level. If it is between 0.625 and 1.625 and 1.3 it is 1.25, yeah, you are smart. 1.25. If it is 0.625 and 1.25, you know it is L1, level 1. Supposing I send 0.75. Let us say there was an noise added, same 0.03 noise was added. Same channel I am sending. So the noise is added as points. So 0.75 is going to be received as 0.78, but it will still be recorded as L1. The effect of noise on a digital transmission is much lower compared to an effect of noise on the analog transmission. Do you understand the point? Since I only have predefined levels as the possible levels, I know it cannot be 1 point, it cannot be 0.75, 0.75, it cannot be 0.78. This guy must have sent 0.625. I don't care whether 0.75 became 0.78, because anyway you sent only 0.625, which is level 0. Unless there is a marginal thing where you are trying to send 1.25 volts, you send 1.24 volts, which is referred to as L0, L1, and 0.3 got added, and even the 0.3 not added. 0.2 got added. Yeah, 1.24 plus 0.2 will be, I will not even say 0.2, 0.01 got added. 1.21 becomes 1.24 becomes 1.25. Then you are not sure whether what is sent was L1 or L2. But occasionally this type of extremities are there. I am not saying it is a perfect transmission. I am saying it is better than analog in noise performance. Correct? That is one of the reasons why we want to go for analog. It can store and reproduce values more, I will not say accurately, I will say reliably. Then, why did I not say accurately? Accuracy depends on the number of levels I use. If I am going to truncate my 0.825 as 0.625, it is not accurate by any stretch of imagination. But I chose to have only 8 levels. If I wanted, I could have 16 levels. If I wanted, I have 256 levels. If I wanted, I can have 1024 levels. That case becomes more and more accurate. Accuracy depends on the number of levels. But so more reliably I can store and reproduce. And more reliably I can transmit and receive. That is one reason. Do you think it is a valid reason, good reason to go for digital? No? You are not convinced? I think it's a good reason. Okay. Now, second reason I would say is this accuracy. I will go back to accuracy a little bit more. I said accuracy can be improved by analog or digital. In a digital case, it is having more number of levels. In analog, it is by giving an instrument which is more accurate, which can handle these lower order values better by increasing the sensitivity of the equipment. For example, a meter, how does it work? A meter works by the coils, which current carrying coil just makes a deflection of the pointer and where it stops. So if I want to make more accurate measurement, I should have more sensitive coils. But now the difference between having more levels and more sensitive analog is very different. To improve the accuracy, it is easier in digital because all I have to do is to increase the number of levels. So reproduction of more levels is the same effort. Hardware wise it is more, but then the similar hardware I have more of it. If I have similar hardware, more of it, I can improve the accuracy of a digital system. In an analog system, to get more accurate, I need to struggle more. I need to slog more. Analog improvement accuracy is more difficult than digital improved accuracy. Digital improved accuracy means more levels, which are identical to the earlier levels. Instead of having 8 of those level determining whatever it is, I will have 16 of those. Whereas analog, I can't say. For example, you know the measurement, if I wanted to make a measurement of the distance from here to here, if I ask you to measure and give me the feet, you will very easily take a foot ruler and measure and say 7 feet, 8 feet. And I ask you to do it in inches, then it will be more careful. You need a scale with an inch, ruler with an inch calibration in it. And then I have to be very careful, and then finally how many? And then if I say, give me the nearest millimeter, then I need an instrument with a millimeter calibration, and then I have to be very careful in my measurement. So my measuring more and more accurately in analog system is more difficult than measuring more and more, having more and more levels and improving the accuracy or precision of a digital system. That is another reason why I want to go for digital. So the cost of the system for more accurate system is proportional to the accuracy in the case of digital, whereas it increases exponentially in the case of analog. In analog, the increase in cost for a more accurate system is not proportional to the accuracy improvement. It is much more than that. In digital, I spend more money, I get similar. If I am happy with 4 levels, be happy. If I want 8 levels, give me double the cost, I will give you. Analog, I can't say that. So it is more difficult to make more meaningful measurements, more accurate measurements in analog compared to digital. Or storage. When I say measurement, it means storage, transmission, everything. The quantity has to be signal. After all, what did I say? The signal has to be represented, stored, measured, transmitted. Everything is part of signal. Let us call it signal handling or signal processing. The signal has to be processed. You can want to call it handling of the signal, doesn't matter to me. So these are the reasons why you go for digital. So now the effort is to convert everything that you see in the world. And why can't we do it everything digital? It is not possible. So I told you why digital. Why do you need analog? If you say so much about digital being so good, can you not do away with analog altogether and have only a digital world and not have the principle of electronics course in your next semester? That's a good, tempting thought, but unfortunately not, because all real life signals are analog signals, be it a temperature variation of a body or a temperature variation of a parameter or anything, or a speech or a light or heart rate or whatever. Think of, have you seen this ECG waveforms in monitors, in hospitals, in movies? Suddenly the heart rate will come and then fellow is dead. That's how they represent a person dying in a movie, isn't it? So all are analog signals, unfortunately. Or fortunately, if you look at the digital analog people, they will say otherwise they won't have jobs. So analog signals are there. And my job, our job is to convert these analog signals to digital signals, and because we live as digital people, so today the technology has improved so much. It is easier to do digital, as I said, it is easier to do digital, cost of the digital becoming lower and lower. So we want to do more and more of digital. So what we do is, we cannot do away with analog, I told you. Earliest possible, first you pick up the signal, analog signal, by a transducer, as I said. Sometimes the signal is so weak you need to amplify it. Before you convert into digital, you need to amplify. Supposing you don't do an amplification, sometimes you get lost. Signal is lost completely. Very, very weak signals. If the signal is not very weak, you can directly convert into digital. So before you take an analog signal, convert it to digital, take an analog, pre-process if necessary, that is if the signal is very weak, convert to digital, process. By process I will put anything, I am not going to put separately store, measure, all that. All of them I combine, manipulate, do whatever you want with that signal. That's called processing. Just storing and reproducing is also processing for me. Okay? That's okay. And then convert it back to analog. This is the flow of any processing today. And because the technology advances, because the digital domain being so dominant today in electronics, they are trying to push as much as possible to digital domain and have as little as possible in analog. So in any system today you design, 90 to 95% of the activity is digital, but that 5 to 10% of the analog is not trivial. Without a proper signal, whatever processing you try to do, that's not going to help you. So do not, I'm not trying to say analog is not important. I'm not trying to say don't learn analog, but more effort is put on digital, more amount of work is done in digital domain than analog domain. But design efforts are very difficult in analog, as I said. To improve the accuracy in analog is not easy. The digital is easy. So effort wise it may be even equal or slightly different, but done. I'm not saying a triviality in that sense, please. Do not misunderstand me. Do not misquote me to your analog professors and pick up a fight for me with the analog professors who are my colleagues here. Right? I'm not saying that. But digital has a lot of these applications today. And what we will be seeing only this. We are not going to do this crosses, convert to digital, convert to analog, and all that we will learn later on in future courses. In this particular course, what is the signal? How are the signals represented digital? Or how are we going to use it in processing? What are the various things we can do? What are the various things you can do with the signal? This is a basic building block. So what we will basically study in this course are building blocks of digital circuits and systems. There are several things, we will not go into details. We will have to do both from the analysis point of view. We have to analyze these building blocks, how behavior of them. How does it work? What is the building block? How do you define the input-output relationship of this? How do you analyze it? How to use it? Analysis, use, and design. How do you design it? To build one. That is the crux of the subject matter of this course. We will go into the details of subject matter. There is can be further divided into combinational circuits and sequential circuits and all that. We will see them as we go along. So basically, we will look at the basic building blocks of digital systems and digital circuits, find out their behavior, how they are built, and how to use them in known applications. And in a reverse mode, given a requirement in a digital system, how do you go about designing the requirements of what are the building blocks you need and how to connect them in properly. That is why I call the design phase. Design is, given the specification of a circuit, how are you going to connect, how are you going to choose the proper building blocks, how are you going to connect them together, how are you going to make it work and give you the satisfactory results. And there are two types of circuits basically. One is called combinational, the other is sequential. Both come under the same digital category. I will define the difference between these two a little later on. So in a nutshell, if you want to know the course content of this course, we will be doing the analysis, use and design of combinational sequential building blocks which are required for digital circuits and systems. One sentence course formulation. Okay? And what are the books we will be using? A very good book is called Digital Design by Maurice Mano. M. Mano is called. I don't know, Maurice M. Mano. This is a print all book, I think. It's come in cheap edition, it's available. I think it's available in our bookstores. This Maurice Mano has come through several iterations. It has been there for a while. For the last 20 years, this person has been writing books and updating and improving the contents. The one is the latest edition. It's called third edition, Digital Design Edition 3. Then we have Roth Jr., C.H. Roth. Fundamentals of Logic Design. By C.H. Roth. It's called Jayco Publishers. I don't know what it is. Jayco Publishers, 1998. There are only two typical books. There are so many books. Any book which has a title like a digital design, logic design, digital and logic design, digital circuits, good enough. Because these are all very basic stuff we are talking about, the basics, first introductory material. On digital, there are scores of books, at least about 15, 20 good books you can see in library, any library. And I will not be following one book strictly. I would like to teach you everything that you need to know in a first level course, but does not mean that you will be following a book from cover to cover. It is not necessary because this is such an interesting course. We have been teaching this course for a while, so a lot of other topics from different things. Some book doesn't cover one topic very well. Some book does not cover a topic at all properly. So in that case, I will go on. I don't have to now even follow books because I have been teaching this course so many times. So I just sort of give an essence of my experience of teaching this course over years, and it has been a good practice. I have been doing it for a while and without any much complaints. So that's what we will do, but you need to have a book so that you know how to follow the flow of the material and do more studies. Sometimes the topic which is we are not spending enough time in the classroom, you may want to do further studies. Sometimes something is not very clearly explained in the class, you may want to go back and refer to a book. So please have a book. I am not saying you should not have a book, but do not expect me to follow a book from page to page. And it's always nice to have a basic digital book, because this is a first course. A lot of other things are done. As I said, today digital world is technologically very advanced world. So lots of opportunities for you to do digital. There may be an advanced course in digital we will do, maybe some project, mini project you may be doing, there may be even a major project you will be doing in digital area. So it's always nice to have a reference book with you instead of always having to borrow or copy somebody else's book and all that. So if you are thinking of buying a book, you can buy one of these two books. And there are so many others also. You can also, if you want to have any particulars, doubt about a particular book is good or not, you can always ask me. You can also browse through that and tell you. So these are the various things we need to know, and as we go on we will develop material, and for homework maybe I may have to prescribe from some of these books. So that may be a good idea to give you that way, to have at least there must be enough number of books available so that you know what problems are there for the class. Okay, this is where we will stop today, and in the next lectures we will start with the detailed subject matter. Digital, I said the levels and all that, we have to be a little more specific. How do you represent levels? What do you mean by level? So what is a digital signal? How do you represent digital signals? And then we will start with the simple gates and then move on. Are there any questions? Any questions? So it's a good idea to have a book and follow the book, read the book, sometimes ahead of the class. Better to read it ahead of the class if possible, so that way you can understand the topic better. And any questions, feel free to ask me. Don't worry about this being a studio setup. You can always ask me questions. You can have interactive, no problem. And then I'll prescribe homeworks from the book so that you can start also working out problems. Okay, we'll stop here for today.
Thank you.